Evaluate the vector line integral over C of the vector field dotted with the differential d vector r, where we have the vector field defined by the components 3x squared y squared and 2x squared y minus 4, and C runs from the point 1, 2 to negative 1, 1. So here is a little hint to help us get started. The first thing we want to do with a problem of this nature is to check if the vector field f is a conservative vector field. And why? Well, the fundamental theorem of line integrals tells us the following. So if we have a conservative vector field, or if we're able to write this vector field as the gradient of phi, then the fundamental theorem of line integrals tells us that this integral is path independent. Or in other words, a parameterization of C is not needed. We simply need to evaluate the potential function phi at the endpoints. All right, so the first thing that we're going to do is apply a test for conservative vector fields in R2. So if you look back to our given vector field up here, you can see that we have two components. We have our F component and our G component. So we have that the F component is defined as 3x squared y squared, and that the G component here is defined as 2x cubed y minus 4. And so taking the partial derivative of f with respect to y, we are left with 6x squared y. And then taking the partial derivative of g with respect to x, this too leaves us with 6x squared y. So we're very excited. We have that therefore, since the partial derivative of f with respect to y is equal to the partial derivative of g with respect to x, we know that f is conservative. Or in other words, there exists a potential function phi of xy such that our vector field can be written as the gradient of phi. So our next order of business is to find this potential function. And again, to get us started here, we've just shown that f is conservative, our vector field is conservative, so its components are the partial derivatives of the potential function phi. So we have 3x squared y squared 2x cubed. Let's give ourselves a little bit more room here. 2x cubed y minus 4. And there's a couple of different ways to get started here. But the first thing that we want to do is pick one of the partial derivatives. So I'm going to choose the partial derivative of phi with respect to x. And we want to integrate this partial derivative. So integrate the partial derivative of phi with respect to x with respect to x to find the potential function phi of xy. And we want to note that this includes the arbitrary function c of y. So we need to include our arbitrary function here because we have a multivariable function. So we have phi of xy is equivalent to the integral of the partial derivative of phi with respect to x dx. So this is the integral of 3x squared y squared dx, which leaves us with x cubed times y squared plus the arbitrary constant function c of y, or just the arbitrary function c of y. So thus far we have our initial potential function as x cubed y squared plus c of y. And we think to ourselves, well, what is c of y? So that's our next order of business. To find this constant function, we want to compute the partial derivative of phi with respect to y, and then equate it to g. And if you're asking yourself, why are we equating it to g, we want to keep in mind here, we know that f, again, is conservative. So this means that the components of our vector field fg are equivalent to the components of the gradient of phi. So our function, or excuse me, the component g is equivalent to the partial derivative of phi with respect to y. So we take the derivative of the potential function, or the initial potential function we found in step 1, so this leaves us with the partial derivative of phi with respect to y is equal to 2x cubed y plus c prime of y. Again, since the partial derivative of phi with respect to y is equal to g, we have 2x cubed y plus c prime of y is equal to 2x cubed y minus 4. And solving for c prime of y, we subtract 2x cubed y from both sides, leaving us with the partial, or the derivative of this function with respect to y is just equal to negative 4. And so we're now ready to go ahead and find c of y by integrating this derivative with respect to y. So we have c of y is going to be equal to the integral of the derivative c prime of y dy, which we know is going to be the integral of negative 4 dy. I have minus 4y plus c. So we have successfully found the arbitrary function c of y to be negative 4y plus c. And now we can go ahead and we'll substitute this back into the potential function we found way back here in step 1. We can say, therefore, our potential function, phi of xy, is going to be equal to x cubed y squared plus, so it's actually going to be minus 4y plus c. And so this is hopefully going to be our beautiful final answer. And to make sure that we get this right, let's double check by differentiating. So we want to double check here. So we want to check our potential function by finding the gradient. That's a surefire way to make sure you get this question right. So using that potential function, if we take the partial derivative of it with respect to x, this leaves us with 3x squared y squared, and the minus 4y goes to 0, plus c goes to 0. Partial derivative of phi with respect to y leaves us with 2x cubed y minus 4. And we are delighted here because we see that this is equal to, or the partial derivative of phi with respect to x is equal to the first component, or the f component of our vector field. and that the partial derivative of phi with respect to y is equal to the g component of our vector field. So this is, in fact, our beautiful final answer. But we're not done yet. Now that we've double-checked our potential function, we're ready to evaluate. Again, remember, we were asked at the beginning to evaluate the line integral of the vector field dot the differential d vector r. And we're going to use, or using, the fundamental theorem of line integrals. And let's keep in mind here, what were our initial points? So we'll say we have our point A is defined as 1, 2, and our point B is being defined here as negative 1, 1. So by the fundamental theorem of line integrals, we know that this line integral of the vector field, because our vector field is conservative, it's immediately equal to the potential function, which we'll evaluate from point A to point B. And plugging in what we just found, this is going to be x cubed y squared minus 4y plus c. And we are evaluating from the point 1, 2 to negative 1, 1. So you can plug these points right in. So with our first point, we have x is negative 1, so I have negative 1 cubed multiplied by positive 1 squared minus 4 times positive 1 plus c minus, now we have 1 cubed multiplied by 2 squared minus 4 times 2 plus c. So let's see, we can simplify this a little bit. We have minus 1 minus 4 plus c in our first evaluation. And then in our second evaluation, we have 4 minus 8 plus c. So this leaves us with a negative 5 plus c minus a negative 4 plus c. And if we distribute our negative through here, we see we have some beautiful cancellations. So we have negative 5. The c's will cancel out, plus 4, leaving us with our beautiful final answer of negative 1.